Module 2B. Here we'll investigate 3 more physical properties of sound. Before continuing, however, consider how fast does sound travel? How are frequency and wavelength related? What does the term inversely mean? And from the 1979 movie Alien, in space, no one can hear you scream. If that's true, why? In Module 2A, we investigated amplitude, or the intensity of change of a sound wave, and frequency, the rate of change of a sound wave. In this module, we'll investigate velocity, how fast sound travels, wavelength, the physical length of a sound wave, and phase, timing between waves, or the point where a sine wave is in completion of a single cycle. So let's investigate velocity. Velocity is the speed at which a sound wave moves through a medium. If the medium is air at standard temperature and pressure, sound travels at 1,130 feet per second. That's 1,130 feet every second. As we'll see, however, the more dense the medium, the faster the velocity of sound. Here's an illustration of how the velocity of sound is different through 3 different media: air, water, and steel. The hammer on the left will strike the plate and cause a sound wave to travel the distance that we select, 343 meters. Okay, we strike the hammer, and we notice it takes 1 second for the sound to travel through air, but it takes less than 1/4 of a second to travel through water, and almost no time at all to travel through steel. That went by pretty fast. Let's set our distance 10 times as long. 3,443 meters. That'll be about 10 seconds. Okay, strike the hammer again, and this time we see that it takes quite a bit longer for the sound wave to travel through air. And we see 10 seconds through air, 2¼ seconds through water, and less than a second through steel. So we see the more dense the medium, the faster the velocity of sound. Okay, so now we understand amplitude, intensity of change, frequency, rate of change, velocity, speed of travel. Let's investigate wavelength, the physical length of a sound wave. To define it, wavelength is the distance the sound has traveled in one cycle of its frequency. We'll see that wavelength is inversely proportional to frequency, which means that as wavelength goes up, frequency goes down. Or the lower the frequency, the longer the wavelength. We'll notice that the distance the sound has traveled in the time it takes to complete one complete cycle is the wavelength of the sound. We'll identify wavelength as the Greek letter lambda. Notice on a frequency that's much higher, the wavelength is much shorter. The higher frequency takes much less time to complete one cycle, and therefore its wavelength is shorter. It's fairly easy to find the wavelength of a sound at a particular frequency simply by dividing the speed of sound by the frequency of the sound. For example, what is the wavelength of a sound in air whose frequency is 1,000 hertz, 1,000 cycles every second? Setting up a simple equation, our wavelength lambda is equal to 1,130 feet per second divided by 1,000 cycles per second. Since we have per seconds in the top and the bottom, they'll cancel each other out, and we're left with 1,130 divided by 1,000, a simple move of 3 decimal places, and we see that the wavelength of 1,000 hertz is 1.13 feet per cycle, or simply 1.13 feet, with cycle understood by the definition of wavelength. So in our example, if the frequency was 1,000 hertz, we see that its wavelength, lambda, is equal to 1.13 feet. Or, by the time the sound has traveled one cycle, the sound has moved 1 0.13 feet. The concept of wavelength becomes much more important when we look at acoustics. Okay, let's tick them off. Amplitude, intensity, frequency, rate of change, velocity, speed of travel, wavelength, physical length of the sound wave. The last one, phase, is timing of a sound wave. Acoustical phase represents the time relationship between two or more sound waves, or it is how far a single sound wave has progressed through a single cycle of its frequency. Some of the aspects of acoustical phase is we measure it in degrees. Two sound waves that are in phase reinforce each other, and two sound waves out of phase cancel each other. We said we measure acoustical phase in degrees. What we're really measuring is the phase angle of the sound wave. When we say degrees, we don't mean degrees of temperature, but degrees around the circumference of a circle. Imagine a compass. You might think of looking due north as being 0 degrees on the compass. If you turn and face the east, you have turned 90 degrees. Turning to the south, you've completed 180 degrees of rotation. To the west, 270 degrees. And turning all the way back to north again, you've moved 360 degrees around the circle. So a turning circle generates a waveform with corresponding angular measurements. Here we see a circle rotating, generating a cosine wave. So phase angle measures where a sound wave is in completion of one cycle of its frequency. If we consider two sound waves of the same frequency and amplitude, if they both start at the same time, they will be in phase and their amplitudes will add together. The result is a single sound with twice the amplitude of the original sounds. If, however, the sine waves are 180 degrees out of phase, that is, one is going negative while the other is going positive, then the amplitudes of the sound waves will cancel each other out, because they're going in the opposite directions. One is pushing while the other is pulling. Here we see two sound waves that are 90 degrees out of phase. Two sound waves can be out of phase by any amount. Let's demonstrate this with two actual sound waves. Notice that as the sound waves become more out of phase, the sound amplitude becomes less and less. So there we have all five physical properties of a sound wave: amplitude, the intensity of the sound level change, frequency, how fast the sound is changing, velocity, how fast the sound is moving through a medium, wavelength, the physical length of a single cycle of a sound wave, and phase, timing between waves, or how far the sound has moved through a single cycle of its frequency. Before continuing, can you describe the five physical properties of sound? What two physical properties are related to each other, and how are they related? Which physical property can involve more than one sound? Next, in Module 3, you'll investigate much more deeply measuring amplitude, the decibel, sound pressure level. We'll investigate different bands of frequencies, talk about fundamentals, harmonics, overtones, and finally we'll discuss a very important relationship between frequency and loudness. Did you think that frequency was not related to amplitude? Well, we'll investigate what's called the equal loudness principle, a very important concept. We'll finish off Module 3 with masking, timbre, and the sound envelope.